Today I'm going to explain how current and voltage work in a circuit. And to help me do that, I'm using a FET simulator. You can download the simulator yourself from the FET website. It's called the Circuit Construction Kit. And using the simulator you can put together components into a circuit and investigate how circuits behave for yourself. We're going to start by considering current. And I'd like to remind you that current is the rate of flow of charge in a circuit. And the charge in this circuit is represented by little blue spheres. When we close the switch and complete the circuit, we can see that these charges begin to move, and it's the rate of movement of these charges that we call the current. So in this case, we've got a current of 1.00 amps, and on the other ammeter it also says a current of 1.00 amps. I'd like you to consider the bulb as one point on the circuit, and the current entering that point on the circuit is the same as the current leaving that point on the circuit. And it doesn't matter how much current there is, the current before, the current entering that point on the circuit, is the same as the current leaving that point on the circuit. And I can demonstrate that by changing the voltage, and because the resistance in the circuit stays constant, by increasing the voltage we increase current as well. So here I'm just going to bump up the voltage a bit, and we can see now that the current before the point that we're considering on the circuit, the bulb, is 2.18 amps, and the current after that point in the circuit is 2.18 amps as well. If we adjust the current again, we have 3.71 amps entering the point on the circuit, 3.71 amps leaving that point on the circuit. I've put together a circuit with two bulbs and with 4 ammeters, and it doesn't matter whether we consider the bulb to be the point or whether we consider a section of wire to be that point. The current entering the point is always the same as the current leaving the point. So in this case, this little section of wire, there's no bulb here. We have 0.45 amps entering and 0.45 amps leaving. This circuit has multiple pathways, 2 pathways that the charges can take. The charges can go along this first pathway, or they can go along the second pathway down here. And we call these different pathways branches. So we've got 2 branches that the charges can take. Now, does our rule still apply? Well, we can see that if we consider this junction as our point on the circuit, and we said before that the current entering that point will be the same as the current leaving that point. So the current coming into that point is 1.35 amps. And then we've got 0.45 amps coming along the first branch and 0.90 amps coming down the second branch. If we add the 0.45 amps to the 0.90 amps, we find that the total is 1.35 amps. So the total current exiting this point on the circuit is the same as the total current entering it. So as we saw before, total current in equals total current out, and the rule still holds true. So let's try an example. So we've got 2.5 amps in, 2 amps out, but we don't know what current is along this branch here. We can use the rule total current in equals total current out to work it out, and so you can probably see that the difference between 2 and 2.5 is 0.5 amps, and we could also do 2.5 minus 2 equals 0.5 amps. So we'd expect there to be 0.5 amps of current along this branch. Let's see if that's correct. And you can see indeed there is 0.5 amps of current along this branch. So 2.5 amps in, 2 amps along the bottom branch. That means there must be 0.5 amps along this middle branch. Let's try another example. Now this time we have 0.7 amps along this branch and 1.4 amps of current in this branch. And we want to know how much is coming into that point. So total current in equals total current out of that point. If we add together these 2 currents, then we should have the total current in. So 0.7 plus 1.4 equals 2.1 amps. So we'd expect there to be 2.1 amps of current coming in here. Let's check to see if that's correct. And there we go, you can see 2.1 amps of current here. This time I've reversed the direction of the supply, and so the current is going in the opposite direction. So considering this junction again as our point, we have 0.3 amps going in, 0.75 amps going in, and so we can predict what the total current out will be. 0.3 plus 0.75 is 1.05. Let's just check if that is indeed the current in this part of the circuit. So we'll insert an ammeter, bring that down, connect the wires, and there we have it, 1.05 amps. So here we've got 0.4 amps in to this junction on the circuit and 0.2 amps in. So 0.2 plus 0.4 is 0.6 amps, and that's the current that's coming out along here. So the current law states that the total current entering any point on the circuit will be the same as the total current leaving that point on the circuit.